Welcome back. We're going to be looking at the calculations that are possible for various orders of reaction. I had earlier jotted out the questions to make it very easy for all of us. So if you look at this question here, they said calculate the amount of 0.8 mole per liter ammonia left after 300 seconds if the rate constant for the reaction is 2.66 times 10 raised to the power minus 3 mole per liters per second, and also calculate the half-life. Now there is something I would like to point out here. If you could recall when I gave us the integrated rate law for the various orders of reaction, I told us that that particular formula is what we're going to be making use of to calculate to carry out calculations under this particular topic. Okay, so if you look at this, they gave us the initial concentration. Okay, now if you look at this now, let's take it out. In this question, it was not mentioned whether it's zero order, first order, or second order, as the case may be. But if you could recall what I told us earlier, that with the help of the rate constant unit, you can easily tell if a reaction falls under first, second, or third order, or zero order, as the case may be. And if you look at this, I said rate constant is 2.66 times 10 raised to the power minus 3 mole per liters per second. Now from the units, it is a zero order reaction. If you could recall, zero order reaction has a unit of this. Now the time they gave us 300 seconds, the initial concentration A0 is this, and of course we are asked to find the final concentration. Now I said from the unit of the rate constant, the reaction is said to be a zero order reaction. Okay, now so since we've actually found that the reaction is a zero order reaction, what we are going to do next is to use the zero order integrated formula. Now somebody may ask, how do we know when to use this formula? It's very simple, right? Integrated formulas for 0, first, second has 4 parameters: initial concentration, final concentration, rate constant, and time. Amongst these 4 parameters, they will always give us 3. So if you look at this question, they gave us 3 of those parameters, so you have to find for the final concentration, knowing fully well, oh fine, I'm going to make use of the integrated form. But do not forget that if you're making use of the integrated form, you must use a formula that corresponds to the order of the reaction. Okay, so for zero order reaction, this is the integrated formula. A0 equals to AT. This is initial concentration at time t equals to 0, and this is the final concentration at time t equals to whatever time that was given to us in the question, plus rate constant, which is k times the time. Now initial concentration they gave us to be 0.8, rate constant they gave us to be 2.66 times 10 to the power minus 3, the time they gave us to be 300 seconds, and this final concentration is what we are looking at for. So we say since AT is what we are looking for, you make this subject of the formula. If you keep this one constant and bring this kt to the left hand side, this sign becomes negative. So this is what we have here. So anywhere we see A0, we insert 0.8 mole per liter minus, I open a bracket since I have to multiply these two, right? Our k is 2.66 times 10 to the power minus 3, which is this, times 300 seconds. This 300 seconds. You close the bracket. If you evaluate this, you're going to get 0.798 mole per liters. Right? When you subtract this 0.798 from 0.8, you're going to have 0.002. So when you put it in a standard form, you have 2 times 10 raised to the power 3 minus 3 mole per liter. So therefore, the final concentration corresponds to the amount that will be left after 300 seconds. So this becomes our final concentration. Okay, if you actually want to maybe go through, you can pause the video or you fast back the video to actually check it out. Okay, remember the question said we should calculate for the amount that will be left, that's the final concentration after 300 seconds, and also we should calculate for the half-life. Okay, now since the reaction is a zero order reaction, do not forget that half-life formula varies for the different orders of reaction. Okay, for a zero order reaction, the half-life formula is different from that of a first order reaction. Okay, so in this question is a zero order reaction, the half-life for a zero order reaction is A0 all over 2K. All right, where the A naught is initial concentration and the K is a rate constant. So when you insert this here, A naught they give us to be 0.8, the initial concentration, 2 times K. Our K they give us to be this 2.66 times 10 to the power minus 3. If you insert it here, you get your answer to be 150 seconds. So that is how we got the half-life for that particular question. Okay, now let's look at this next question here. They said a general reaction that occurs at a rate that appears independent. This is appears, that appears independent of the concentration of the reactant are called dash. The answer is zero order reaction. Now what are they trying to say here? If you can remember, for a zero order reaction, rate law equals to this, raised to the power of 0. Anything raised to the power of 0 is 1, so therefore R becomes K. So the rate law for a zero order reaction is independent of the initial concentration, because this concentration will be raised to 0. Anything raised to the power of 0 is 1. 1 times K is K. So in a formula for rate law for a zero order reaction, concentration does not appear in it. So that is why they said a general reaction that occurs at a rate that appears independent of the concentration of the reactant, of course, it is a zero order reaction. Take note of that. I could remember I stated that in the previous videos. Okay, so that's question 2. Let's look at question 3. Now, looking at the next question, question number 3, that says cyclobutane decomposes at 100 degrees Celsius to 2 moles of ethylene with a rate constant 87 per second. Okay, if you look at the unit of this rate constant, of course, this is a unit of a first order rate constant, if you could recall. Okay, question A said if the initial concentration of cyclobutane is 2.0 molar. If the initial concentration of cyclobutane is 2.0 molar, what is the concentration after 0.01 seconds? That's the first question. In this particular question now, the initial concentration is given to us to be 2.0, and they're asking us to find the concentration after this time, which is we are asked to find the final concentration. Question B said, what would be the half-life? Question C is, what fraction in percent of cyclobutane has decomposed in this time? Okay, let's dive into the solution. Now, before we commence the solution, it's quite very important we list out the parameters, what is given to us and what we are asked to find. Now, rate constant K, they gave us to be 87 per second. Alright, so from the unit of the rate constant, it's very obvious that the reaction is a first order reaction. Recall I told us earlier that most of the times they might decide not to mention whether the reaction is a first order or is a second order or is a third order reaction. Okay, they'll just proceed to giving us the rate constant. It is expected that you will make use of the rate constant to get the answer to the to know the order of the reaction. The initial concentration is given to us to be 2.0 molar. The final concentration is given to us to be this is what we are asked to find. Time is 0.01 seconds. Okay, now since we have established the fact that it's a first order reaction, so for the first one, the A part, we said solving for the final concentration, which is our AT. Alright, so using the first order integrated rate equation, remember that this integrated rate equation for various orders of the reaction is actually the equations we're going to be making use of in carrying out calculations. So we have for the first order, there are various ways this particular formula can be expressed, but let's just go with this. We have log AT equals to log A naught minus KT all over 2.303. Now log 8 is actually what we are asked to find. So AT is question mark here, A naught is 2.0 molar, T is 0.010 seconds, our K is 87 per second. Okay, so you're going to insert the parameters into this formula. Log 8 is what we are asked to find, so you leave this one here. log A naught, you insert 2.0 into this place, minus our K is 87 times our time is 0.01 seconds divided by 2.303. Now when you press your calculator, log 2.0 is 0.30103 minus, if you evaluate what we have inside the brackets, we have this. Now this becomes equals to minus, if you actually subtract this from this, this is what you're going to have. So log 80 is equals to minus 0.07674. Okay, so log 80 equals to this. For us to now find the value of 80, we want this 80 to stand alone. We're going to take the anti-log of what we have at the right hand side. Okay, so our 80 becomes equals to, that's the final concentration after 0.01 seconds, equals to 0.84 molar. Okay, so that is that for that first one. Now let's look at the next question. The next question says we should solve for the half-life. Right, remember I told us that half-life for every order of reaction have their different formulas. So for first order formula, for first order reaction, the half-life is 0.693 all over K, where K they gave us to be 87 per second. That's the rate constant. So very simple, insert the K here. So when you insert the rate constant into this formula, we have 7.96 times 10 raised to the power minus 3 seconds. So the half-life becomes 7.96 times 10 raised to the power minus 3 seconds. Now this C is a what fraction in percent of cyclobutane decomposed in this time. Now what they are asking us is that what amount reacted. Alright, so for us to know the amount that decomposed would be the initial amount, which was 2.0 molar, minus the amount that is remaining. Okay, so the amount that is remaining, if you subtract it from the initial amount, it will give us what's reacted or what had decomposed. So the answer to that question becomes 1.16 molar. So 1.16 molar was what was decomposed. Okay, so for us to now solve the fraction, they now say fraction in percent, okay, of cyclobutane that are decomposed. So the formula is amount decomposed all over the initial amount times 100. Amount decomposed is 1.16. From here, 1.16 divided by 2.0 times 100. So that gives us 58%. Okay, now what if you were asked to give the fraction of cyclobutane that has decomposed? If you're asked to give the fraction, not percentage, all right, fraction would have simply been, you would have excluded, if it is fraction, you won't add this 100 because this 100 is why it is percentage. So if it is just fraction, you just say 1.16 divided by 2.0, that gives us 0.58. So this is a fraction. Okay, so that is that for that question number 3. So let's look at the next question here. Question number 4. They say the reaction 2NOBr giving rise to 2NO plus Br2 has a rate constant of this. Once again, if you look at the unit of this rate constant, it's actually shouting second order reaction. So from the unit of the rate constant, it's very obvious that the reaction is a second order reaction. Okay, now they said if the initial concentration of NOBr is 7.5 times 10 raised to the power minus 3 molar, how much NOBr will be left after a reaction of 10 minutes? Determine the half-life of the reaction. Now it's very important for us to know that this time around they decided to give us a reaction, and if you notice, when we actually coined the formula for various integrated formulas for various orders of reaction, we used A. A was simply because we assumed A to be the reactant, but in this case now they now give us a real reactant, so there's nothing wrong there. You can decide to use this, you can just decide to use your A. So I said the reactant in this case is NOBr. Okay, so to actually make it to be very easy for us to avoid confusion, I'll say let's represent the reactant as A. All right, so let's represent the reactant as A. So the initial concentration of the reactant, so in place of NOBr, we're just going to represent it as A so that we can just continue using this A naught to avoid confusion. Initial concentration A naught equals to 7.5 times 10 raised to the power of minus 3 molar. Rate constant is this. Remember, from the unit is a second order reaction. The time is 10 minutes, but we have to convert it to seconds. Why? Because from the rate constant, the time here was in seconds. What if the rate constant had time in minutes? There will be no need to convert this one to seconds. What determines whether we are going to convert our time is actually dependent on the unit of time in the rate constant. This rate constant is a constant, so you actually make sure every other unit corresponds to this. Because this time in this rate constant is in seconds, that is why we are going to convert this minute to seconds. What if this time here was in hours? We would have converted this minute to hours. What if this second here was in minutes? There will be no need to convert, we just use the 10 minutes, okay? Alright, so if you convert 10 minutes to seconds, that gives us 600 seconds. Alright, so let's proceed. So final concentration, question mark. So let's solve. Now, using a second order integrated rate law. A second order integrated rate law is 1 over AT minus 1 over A naught equals to KT. Alright, now this is what I'm looking for, final concentration. Remember, this is what we have to find. So I have 1 over 7.5. 7.5 times 10 to the power minus 3 was the initial concentration that was given to us. Okay, so you just come here. Anyway, you see the A naught, you put 7.5 times 10 to the power minus 3 equals to our K, rate constant, they gave us to be 0.810 times our T, they gave us to be 10 minutes, but we converted it to seconds and it gave us 600 seconds. Okay, so if you make this one subject of a formula, this negative everything here comes over to this other side, we'll have this. When you evaluate here, we have 691.33. So 1 over 80 equals to 691.33. Okay, for me to now get my 80, because this is what I'm asked to find, I'll take the reciprocal of this. So this becomes 1 over this to give us, so this is the final concentration. Okay, so you can pause the video and of course check it out for yourself. Okay, now let's look at the next question. Under this question, they asked us also to solve for the half-life. Okay, if you could recall, I told us, and I'm still going to keep saying it, that half-life or for various orders of reaction have different formulas. Okay, this particular formula is that of a second order reaction. So K half equals to 1 over K concentration of initial concentration of this. All right, so our K is the rate constant, which was given to us to be 7.5 times 10 raised to the power minus 3 per mole liters per second. Initial concentration, they gave us the 0.810 mole per liters. Okay, so T half equals to 1 all over, anyway you see K, you put 7.5 times 10 to the power minus 3 times, anyway you see A naught, you put 0.810. So the answer becomes 164.609 seconds. Okay, so if we go through this, it's very simple. All right, so you can just check out, I'll drop some questions for us to attempt at the end of this chapter. So after now, we are moving next to effect of temperature on rates of reaction. Okay, up next, we're looking at effect of temperature on rate of reaction. That will be the last topic for chapter 1. Okay, one of the factors that affects rate of chemical reaction is temperature. Okay, it's a common knowledge that if you increase temperature of a substance or of a reaction, the reaction goes faster. Take for example the solution of sugar in water. If you dissolve sugar, a cube of sugar, inside cold water and hot water, you realize that the sugar inside the hot water dissolves faster, okay, as compared to that of the cold water, because when you increase the temperature, you're increasing the average kinetic energy of that substance. Okay, so I said here from experiment, rate of chemical reaction doubles if temperature is increased by 10 degrees Celsius. It simply means that if you increase temperature by 10 degrees Celsius, of course, the rate of reaction will be times 2 of what it was initially. So therefore, decrease or increase in temperature affects the overall rate of a chemical reaction. Okay, a formula was proposed by Arrhenius, okay, to relate rate constants and temperature. So we have log K equals to log A minus EA over 2.303 RT. The K is the rate constant, the A is frequency factor, the EA is an acronym for activation energy or energy of activation. Okay, now, but this most of the times, this formula is not always used like this. It's possible we can use it like this. It's often very rare, but majority of times, this one here in the red ink is overall is the final formula. How did we get that? We said for two rate constants K1 and K2 at two different temperature, T1 and T2. Okay, K1 at T1, K2 at T2. So I'm going to rewrite the previous equation. In terms of condition 1 and condition 2. So for log K1, we have log A minus EA all over 2.303 RT1, and log K2 we have this. Okay, so when we subtract equation 1 from equation 2, we're gonna have this. Okay, so it becomes log K1 subtract from this, we have log K2 minus K1, log A subtract from log A, that is 0, hence that's the reason why we do not have it here. Okay, now if you subtract this from this, this is already minus, so when you say minus minus, we start by saying minus this, everything here, right, minus this, so minus minus becomes plus, so that's why this plus is here, because some persons might be wondering, why do we have plus here? This plus is because of minus, that plus is because of minus minus. Okay, so that's how we got that plus there. Okay, so when you actually say minus minus, it becomes plus, you actually rearrange, this comes over to this side, this comes over to this side. Now in indices, log as subtraction can be written as division. Okay, so log K2 minus K1 can be written as log K2 divided by log K1. Remember, since both of them we have log, we take one of them out and put it inside a bracket. This is equals to, now you rearrange this, this one here, the positive comes to the right, to the left, the negative goes to the right. Now when you actually collect like terms, when you factorize EA and all over 2.303 are out, we now have 1 over T1 minus 1 over T2. Now how do we get that? Let's take, for example, this becomes this is we have, okay, so basically trying to say, if I have if I want to write this, let me clean up this so that I will explain this much better for us to understand. Now this simply becomes EA 2. We have, sorry about that, we have okay, so when you make this subject of the formula, we have make EA over 2.303 R subject of the formula. This becomes 1 over T1 minus 1 over T2. So that's how we actually arrived at this. Okay, so this formula is what we are going to be using to carry out calculations. Okay, so I had to rewrite the formula here. I said log K2 over K1 equals to this. So this is the formula we need. Most of the times we have 1, 2, 3, 4, 5, 6. We have 6 parameters. The rate constant 1 and 2, activation energy, gas constant. This R is gas constant. Please take note, this R is gas constant. Okay. This R here is gas constant, always 8.314. All right. So this is T1, T2. Now this formula is mostly used when you are asked to solve the final rate constant K2, when K1 is given, activation energy is given, rate constant. They don't really have to give us rate constant. Sorry, gas constant. This R. They don't have to give us. They will just, you should supposed to know it. This 1 over T1 and 1 over T2. So they will give you this, give you this, give you this, give you one of these, and maybe you ask to find for this. All right. Apart from R, which is a gas constant, they can ask you to find for any one of these parameters. Okay, so this particular 1 over T1 minus 1 over T2 can be rewritten as this. When you take the LCM of what we have in the bracket, T1, T2, you now have this. So you can choose to use this, or you can choose to use the second one, but preferably I prefer the first one. Okay, so what if we want to make activation energy subject of the formula? This is one thing that I used to stress students a lot, to make this in subject of the formula. So I've actually done it in such a way that it will be very easy for all of you. Okay, so if you make it a subject of the formula, this is what you're going to have. So in case you're asked to solve for activation energy, all you just have to do is to insert the values where you have these unknowns. Okay, now let's look at this question. I'm just going to take one question and I will drop question for us to attempt. So if I have this, they say the activation energy of a reaction was found to be 52.04 kilojoules per mole if the rate constant at 40 degrees Celsius is 5.76 times 10 raised to the power of minus 3 mole per liter per second. Calculate the rate constant at this. Now look at this. They give us activation energy. This is what I have here, but I have to convert it to joules per mole. Why? Because our R is always, now this R here, note that R is always 8.314 joules per mole per Kelvin. So this is the value for the R. Okay, now activation energy they gave us in kilojoules. You must convert it to joules so that it will correspond to the joules of this constant. This is a constant, so every other parameter must correspond to this. All right, so this, assuming this was in kilojoules, there won't be need for us to convert, but since this value is always in joules, you must convert this kilojoules to joules. All right, so our activation energy, after when you convert it to joules, is just by multiplying by 1000. Now the first, they give us this rate constant. If the rate constant at 40 degrees is the first temperature, so the rate constant at the first temperature becomes the first rate constant, that's the K1. All right, so at 40 degrees Celsius, this is the first temperature, and this becomes the first rate constant. So we say K1 is equal to 5.76 times 10 raised to the power of minus 3, and T1 is 40 degrees Celsius. Remember, I told us that you must ensure that the temperature matches with what we have here. And also, it's important for us to know that anytime you're given temperature in Celsius, always convert it to Kelvin. Kelvin is the absolute scale of temperature. So when you convert 40 degrees Celsius to Kelvin, it's basically adding 273 to 40. That gives us 313 Kelvin. Now T2 is 55 degrees Celsius, which is adding 273 to 55. That becomes 328 Kelvin. Okay, so we have log K2 over K1 equals to this. Anyway, you see EA, I'm going to insert 52.04 times 10 raised to the power of 3 joules per mole. Okay, now all over 2.303 times R is 8.314, what we have here, and 1 all over our temperature 1 is 313, which is what we have here, minus 1 over T2, temperature 2 is 328, that is what we have here. Okay, so when you evaluate everything inside this bracket, this becomes 1.46 times 10 raised to the power of minus 4, like everything inside this bracket. Press your calculator And of course, outside the brackets, when you actually evaluate this up and down, we have 2717.92. So this multiplied by with this will give us 0.397. So therefore, my log K2 over K1 is equal to this. Do not forget that it's K2 I'm asked to find. So I just have to make sure I'm done. I settled everything on this part before I venture into this. Okay, so log K2 over K1 equals to 0.397. Now recall, for us to make this one to stand alone, anytime anything is attached to a log, you want to get rid of the log and want this particular substance, whatever, to stand alone, you have to take the anti-log of what we have at the other side. So K2 over K1 now becomes anti-log of 0.397, which is 2.4952. Right, so therefore K2 over K1 equals to this. But recall that it was K2 I was asked to find. K1 was given to me. So K2 becomes K1 times this. That gives me K1. I insert the value for K1, which is 5.76 times 10 raised to the power minus 3 times 2.4952. So my K2 becomes 1.44 times 10 raised to the power minus 2 mole per liters per second. Okay, so if you look at this question very well, basically that's the formula, effect of temperature and rate of reaction. They will always give you two rate constants, or the formula involves two rate constant, two temperature, gas constant, activation energy. Aside from gas constant, which is R, they could ask you to solve for any of the other parameters, and of course other ones will be given to you. Okay, so you can always fast back or can always play back the video or pause to check out where you did not really understand very well. Okay, so I have a question here for us to make an attempt. So that I've solved it. We can see verify to check if we're going to get this answer. All right, drop whatever questions you have on the comment section. Okay, please try as much as you can to at least subscribe. Thank you very much. That's the least you could do for us, to just encourage us to subscribe, like, and of course comment on whatever you don't understand. Okay, thank you very much. See you next chapter 2. Okay, please make sure you solve this question. You can drop it on the comment section when you're done. Okay, thank you very much. Please, before you actually leave the channel, please do me a favor and like, subscribe. Thank you very much.